Thank you. Thank you very much. With an introduction like that, it's kind of hard to follow up, I think. But it's great to be here, and it's great to see so many bright, chiming faces, some of whom I've even seen before, and not just the old people, because there's some astronomers here who I'm hoping we can entertain as well. So today I'm going to talk to you about the accelerating universe. The accelerating universe is the thing that won me the Nobel Prize. But to understand the accelerating universe, you have to understand the universe from beginning to end. Now, you have been talking about the very small, it sounds like, for a lot of the week. And nanoscience is great. But sometimes it's good to look at the world from a different perspective. And the one thing you need to realize compared to nanoscience is that the universe is big. Now, we use the speed of light as our guide to understand the universe. And you may recall that light travels at 300,000 kilometers per second. So that is 7.5 times around the Earth each second. And let's take a quick tour. So if we look to the moon, we go out 1.5 light seconds. That means when Neil Armstrong took his one small step and the radio waves were transmitted to Earth, picked up just outside of where I live in Canberra at Honeysuckle Creek, and broadcast to the world, we found out about it 1.5 seconds after he actually did it. That's how far away the moon is. You may not realize it, but the sun is a lot bigger than the moon. It's actually a lot bigger than the Earth-Moon system. It's 5 light seconds across. So it dwarfs. We are dwarfed by the size of this sun. Of course, the reason it appears so far, or so small, is because it's so far away. It's about 8 light minutes in distance. Now, if we go out further to the outer reaches of our solar system, then you reach out about 10 hours to that poor, maligned ex-planet Pluto. So Pluto was discovered, and we'll talk a little bit about it later, in 1930. And then suddenly, in 2006, we decided to call it a dwarf planet. We'll explore that a little bit later. Someone was asking Dr. Kowal and I about the bright star they always saw in the southwest part of the sky. And the star we think the person was referring to, but we're not actually sure, is the nearest star in the sky to the sun, Alpha Centauri. It's the Alpha Centauri solar system. There's actually 3 stars there. And Alpha Centauri is one of the brightest stars in the sky because it is one of the closest stars in the sky. It's a star not dissimilar to the sun. It's 4.3 light years in distance. And it is the brighter of the 2 pointer stars to the Southern Cross. Now let's just do an analogy to get our head around it. We're here in Sydney, and imagine that Alpha Centauri is a P here in this lecture theater. And I want to find out where the sun would be. Well, it turns out the sun, which would be another P, almost exactly the same size as Alpha Centauri, they're very similar stars, would be located at my house in Canberra, with everything in between empty space. So space is very empty. And that's particularly remarkable when you think we live in one of the most exciting places of the universe, a galaxy of 100 billion stars, known as the Milky Way. We're about 30,000 light years out from the center. Now, the Milky Way, of course, is one galaxy, as we call them, of many. If you look out in the southern sky to the south, not too far away from Alpha Centauri, you will see 2 satellite galaxies of the Milky Way, the large and small Magellanic Clouds, 185,000 light years in distance. Who here has seen the large or small Magellanic Clouds? Oh, you're a pretty good audience. Normally only a few people have seen them. So the large Magellanic Cloud is about 10 billion stars, the small about 1 billion stars. Astronomers like to use the word dwarf. We call them dwarf galaxies. The first real galaxy of any size is the Andromeda spiral. It's sort of the sibling of our own Milky Way. It's 2 million light years in distance. You can see it from the southern hemisphere, but it's not easily visible because it's so far north, and it just barely gets above the horizon, except for in the north of the, like up in Darwin, it's not so hard to see. But these are just the tip of the iceberg. If we go and take a picture with the Hubble Space Telescope, and we look at a piece of sky for a month, this is what we see. This is a picture of the sky that is 1/32 millionth of the entire sky. You have to take 32 million pictures like this one, and then you have taken a picture of every piece of the sky. There's about 5,000 galaxies in this image, and they are very far away. The most distant ones, these tiny little smudges, are roughly 12 billion light years in time away. Light takes 12 billion years to reach us. And if we go back even further, because we astronomers like telescopes so we can see further and further, we don't see any more galaxies. Instead, what we see is this. This is an image of what we call the cosmic microwave background. It's an image of the entire sky taken in microwaves. And those microwaves, turn out, were the radiation left over from the universe right after it was created. 380,000 years after the universe was created, this is what the universe looks like. We're looking back almost 13.7 billion years in the past. But we can't look back any further because there's nothing left to see. We literally run out of time itself because the universe, for some reason, got started 13.7 billion years ago in the thing we call the Big Bang. Now, if we want to understand how we've come to these conclusions, let's look at the history of cosmology. The history of cosmology really got its start when we started to be able to use telescopes to train on objects in the sky. And so, for example, if you look at the sun and you take its spectrum, that is, you spread its light out in the colors of the rainbow, you will note from on Earth that every element has a fingerprint of color which uniquely identifies it. It comes out at a very specific wavelength or color of light. And a man, Vesto Melvin Slipher, who here has heard of Vesto Melvin Slipher? John? Anyone else? Bruce? All right, a few, but not many of us. Vesto Melvin Slipher, my hero. When I was your age, he was my hero because his family gave me a scholarship to study at the University of Arizona. I had no idea who he was. It turns out he is the beginning, the person who started observational cosmology. He didn't know it at the time, and what he did is he looked at galaxies, and he took their spectra. In 1916, when he did this work, we did not know what galaxies were. He took their spectra and he said, geez, they're made out of the same thing that the sun is made out of. He could see all the different elements that the sun was made out of, and he saw those same things in these galaxies. But there was a difference. And the difference was that the light was stretched redward of what the sun was. And he said, oh, I know what this means. Light is a wave. And just like sound waves, which we're all very familiar with, where if you have a vehicle moving at some rate relative to the speed of sound, the sound waves get compressed and the pitch is raised, and as the police car, for example, goes by you with their siren on, then the Doppler shift, as we know it, stretches the sound waves, makes them longer, lowers the pitch. Light, of course, is a wave, so the same thing applies. So when you look at a galaxy, and you see a galaxy, for example, moving away from you, then its light will be stretched redward. If it were moving towards you, its light would be compressed blueward. When you take light waves and you compress them, you make them bluer. The more you compress them, you can turn it into ultraviolet and eventually gamma rays. So the funny thing that he saw in 1916 was a mystery. Almost every single galaxy observed was doing the same thing. It was moving away from us. And that begged the question, what's going on? Since the time of Copernicus, we thought we shouldn't be a special place in the universe. And suddenly, we seem to be in a very special place, very unpopular place, which everything's going away from. What would be going on? This was a conundrum of 1916. It was solved by measuring distances. Now, measuring distances in astronomy is not as simple as just laying down a ruler between here and the nearest star or galaxy. That's too far, and so we have to resort to nefarious means, and we astronomers observe the universe, so what we use to measure distances is how things appear. So, for example, if I look at a candle or a ruler, you will note the further away the candle is, the fainter it appears. That, of course, is known as Newton's inverse square law, where if you could take a light bulb and turn it on, and you had, let's say, a photovoltaic detector that measured how bright, how much energy was coming from the light bulb, and then I halve the distance of the light bulb, you get 4 times more light. So all what I need to do is have a really bright light bulb whose wattage I know, and I can measure distances. Well, we don't obviously have that, but we do have stars. And so what Hubble did is he went out and said, I am going to look at how bright stars appear in these galaxies, and I'm going to judge the relative distances of the galaxies. If one galaxy's stars are half as bright, or let's say a quarter as bright as another galaxy's, it's twice as far away. So he did that work, and he had access with the largest telescope in the world at the time, the 100-inch telescope just outside of Los Angeles. He assumed these stars were all the same in each galaxy. It turned out not to be a brilliant conclusion, but it was good enough for astronomers' work, as physicists always like to tell us. And what he found was that the faster the galaxy was moving away, as measured by Slipher, the fainter its stars. Or in other words, the further the galaxy, the faster it was moving. Here's his data. So bright stars here, faint stars here. These are further, these are close. Low redshift, so low stretching, high stretching. And there's this pattern. Further away you go, the faster you're moving away. And from this document, or from this diagram, he announced to the world in 1929 that the universe is expanding. Now, why did he say that? Well, let's expand the universe and look at it. So here's the universe, which thanks to the wonder of my computer, I can expand. So I'm going to expand it. Now let's overlay before and after and see what we see. I overlay before and after, and I see nearby objects moved a little bit, so they would have a low velocity. And the distant objects, they've moved a lot. They would have a high velocity. If we live in an expanding universe, the further away something is, the faster it will be moving, just like Hubble saw. And it turns out it doesn't matter where you are. I can overlay those images anywhere I want, and I see exactly the same thing. Copernicus is safe after all. We're not a special place in the universe. All right. Now, that's a nice cartoon, but it turns out, even better, we have a theory that tells us how this all works. And that theory comes from none other than Albert Einstein. In 1905, Albert Einstein did his great work on special relativity, which gave him E equals mc squared. But in 1907, he had what he described as his greatest thought. And that thought is a little subtle. The thought is that gravity, the acceleration due to gravity, and the acceleration due to moving faster were exactly equivalent. Another way to say that is, imagine you're in a box and you don't know if you're on a rocket or on planet Earth. His theory was, and his assertion, was that there was no experiment you could do from within the box that would tell you if you were on planet Earth or on a rocket ship that was speeding off at 9.8 meters per second squared. Small thought. It took Einstein 8.5 years of working on what this means. And it turns out it means that the universe is really messy and complicated compared to what Newton thought. It means that, for example, space is curved. So rather than the idea that gravity pulls, it really is that gravity disforms space and time. And that's how you have to calculate things. And it made all sorts of predictions. It, for example, told you that Mercury's orbit should be a little affected, and that was already known to be a problem, so he could predict that. But it also predicted that the light would be bent by the curvature of space. So that, for example, if you looked at the sun during an eclipse and you wanted to look there after the eclipse had been done and the sun was out of the way, you can see the stars would be displaced. Now these are the images taken by Arthur Eddington in 1919. He was a theorist. He was not an observer. And there's a moral you will learn out. He was in a place which was kind of cloudy. His images, you'll note you can't see any stars. He hired the observer, Cromwell, who was the astronomer royal, to take images. He was on the other side of the planet. And Cromwell, the guy who was supposed to know what he was doing, didn't manage to get his telescope focused. So all the stars look like donuts here. But this is where the theorist comes in. Theorist Arthur Eddington used this data to figure out whether or not Einstein's theory was correct. And he announced to much fanfare in not so much a scientific journal, but as a newspaper, that this data showed that Newton's laws of gravity were wrong and Einstein's were right. The only problem is that with modern techniques, which were a lot better than they had in 1919, you can't actually reproduce the result with the data because it's not good enough. So Eddington gets a lot of credit for this, for being right for the wrong reason. Sadly enough, the real experiment was done in 1922 here in Australia by two American astronomers, it turns out, who really did do the statistics correctly and showed definitively Einstein was correct. Unfortunately, we didn't realize this discrepancy until about 1980. So that is the way history works. If you're going to be wrong, be right. All right. So one of the interesting things that Einstein could do with this new theory of his is to do something Newton could never do with his theory. And that was to solve cosmology. Imagine you have a universe that goes on forever and ever. How does gravity work? Newton nearly drove himself mad. Having seen Newton's logbooks, he was mad. He was crazy. He did everything out to about 40 decimal places, as many decimal places as he could fit on his paper. So he carried the numbers until he ran out of paper, not for any other reason. I got to see one of his things, journals, where he was trying to figure out how his eye worked. Now, imagine you want to figure out how your eye works. How would you do that? Well, what Newton did is he decided to stick a needle in there and poke it around and see what happened. And so I'm looking at his journal, and there's blood splotches everywhere. And I had to, as some people walked around, sort of go and rethink my lunch for the day. But I did get to handle Newton's blood. So anyway, Newton was an interesting guy. Anyway, Newton could not make his gravity work in a universe that went on without end. The only solution that made sense to him was that the universe had no gravity. There was nothing in the universe. There was no mass. And yet he knew he existed, therefore he had a problem. So the solution came from Einstein, because Einstein's version of gravity had no problem with this. And when he solved it, turns out in 1916 and 1917, he worked on this. One of the first things he did, he got what he considered to be the wrong answer. His theory of general relativity said the universe should be in motion. It should be expanding or contracting. Now, Einstein worried about observations, and he looked around and asked everyone and said, well, is the universe expanding? Everyone said, no, it seems to be static. And he said, we have a problem here. I know this equations are beautiful. They must be right. So he did what any theorist does when their theory is confronted with observations which show the theory to be false. He added a fudge factor. And that fudge factor he called the cosmological constant. It was energy that was part of space itself. And in his equations, energy that is part of space causes gravity to push rather than pull. And so the idea was that the universe would be constructed in his mind with this energy that exactly counteracted the pull of everything in the universe, and he could balance the universe out. There was one problem, is that when people went through and tried to figure out how this would work, it turned out that if a butterfly flapped its wing in one part of the universe, that was enough to set off the entire universe to either start expanding or contracting. We say it's not stable. And so his theory was clearly wrong. Of course, this was all 12 years before Hubble realized the universe really was expanding. And so Einstein later in life described this as his greatest blunder, or the direct German translation, he says, "I acted like a donkey." So Einstein's view of the expanding universe is just a little different than the Doppler shift. When you look at a distant object, and its light is traveling through space, it's traveling through space which itself is expanding. And so the light waves are getting stretched by the expansion of space. It's not so much that the objects are moving away from you, it's rather that space itself is being created between the objects. So the further away you look, the more space is expanded between you, and the more the light is stretched, the faster it appears to be moving if you think of it as the Doppler shift. So imagine you have space being created in a universe, and I run the universe in reverse. What that mean? That means that things are closer and closer and closer, and at some point everything in the universe has to be on top of everything else. That's the idea of the Big Bang. It's almost inevitable. If the universe is expanding, there will be a time in the past when everything will be on top of everything else. The universe will be really, really dense. The Big Bang seems obvious. Why it took us 30 years to figure it out? Well, it didn't. There was a guy by the name of Georges Lemaitre who turns out in 1927 figured out that the universe was expanding, derived all the equations, did this for his PhD, showed Einstein at a conference in Solvay, and Einstein said, "Sir, your mathematics is sound, but your physics is abominable." So he didn't get the credit for the expansion of the universe, even though he did it 2 years earlier than Hubble. To add even more insult to injury, in 1931, he ran the universe in reverse, and he said everything would be on top of each other. There would be this time of the primeval atom, when the universe was all in this tiny little area, be really dense. Again, forgotten. He got that right in 1931. Another famous astronomer, George Gamow, got it right in 1948. But the Nobel Prize for this work was done in 1964 by people who had forgotten all this previous work. Fortunately, with Wikipedia and Google, this will never happen again. Well, maybe it will. It's easy to ignore people, even on the internet. So, let's graphically plot what's going on with the universe. Imagine I have two objects separated by some distance now, and I run the universe in reverse. So the dotted line is the trajectory of the universe. The slope of that line is how fast the universe is expanding right now. And so just like two trains going away from each other from Sydney to Melbourne, and they're going this fast apart, you can figure out when they would have crossed each other's path. That's what we're doing here. So the universe, this is age, or the time of the Big Bang, can be figured out from how old you think the universe is. This was such an interesting thing that when I went off to do my PhD, I said, measuring how old the universe is, man, that's the biggest question there is in cosmology. So here I am, 3 years, 11 months, and 4 days, but I wasn't counting, after I started my PhD, with my PhD supervisor, having measured how fast the universe was expanding. And the number I got was that if I put it to the age of the universe was about 14 billion years old. Now, I wasn't the only one working on this. Professor John Graham up there was on a team that had huge amounts of HST, the Hubble Space Telescope time. And he used to come and visit Mount Stromlo when I was first here. because they were working on measuring this. And when they finally got the answer, my number was in the units of the Hubble constant, 73, and they got 72. And Jeremy Mould, who was one of the leaders of that team, told me, yeah, you can keep your thesis now, you've got the right answer. So the answer was actually done using the Hubble Space Telescope. That was the answer everyone settled on and believed. So anyway, now let's think about what this means. We have this universe where we're running it back in reverse, but there's a little problem. The universe might have gravity. So imagine the universe has gravity. That means the expansion rate of the universe is going to change over time. The universe would be expanding faster in the past and slow down, not dissimilar to if I throw a ball up in the air, gravity slows that ball down, makes it travel slower. The universe would slow down over time. So the universe might not be as old as we think. We know there's some gravity in the universe, so the universe has got to be, we would think, a little older, or a little younger than 14 billion years old. But we didn't really know how much stuff there was in the universe. That was a problem. So for a perfectly reasonable amount of stuff in the universe, like this amount, the universe might only be 9 billion years old, 9.5 billion years old. Now, we astronomers are not too fussy, but we do like the universe to be older than the stuff in it. And that was a problem, that value of 9.5 billion years old, because we knew the oldest stars in the universe were at least 12 billion years old. So I was on my way to Australia, and I thought this could be interesting. And it was particularly interesting because we could then think about the future. Imagine a universe which isn't slowing down and has very little gravity. The universe gets bigger and bigger and bigger and bigger forever and ever. It's a universe without end. It lasts forever. On the other hand, a universe that has a lot of stuff in it, well, if it has enough stuff, it'll reach a maximum size and then start to contract. Just like if I throw a ball up here in the room with lower than the escape velocity, it's going to do an arc and come down to ground, not dissimilar to what the universe would do. So if we can figure out what's going on, we can figure out what's going in the future. So both these universes start with the Big Bang, but only the second one ends with a Gnab Gib. That's the Big Bang backwards. All right. Now, as a review, the slowing down of the universe tells us how old we think the universe is. It tells us the ultimate fate of the universe. And it turns out it tells us the shape and the weight of the universe. Because remember, gravity bends space. So if I have a universe that's heavy, space literally gets bent onto itself. And the universe is not just finite in the future, it's finite in volume. What's that mean? It means that if I stand here in this universe that has a lot of stuff in it, space will bend onto itself in the shape of like a sphere or the Earth. The universe, if I start here and I head out that way, I'll eventually come back to where I stand. You say, how the heck does that work? Well, it's sort of the same idea that when people talked to Christopher Columbus and they said, if you head out that way, how are you going to come back? They hadn't thought about space bending in the Earth bending in the third dimension. Well, space is bending in the fourth dimension, one related to time. Now, if you're having trouble visualizing 4 dimensions, it's okay. I have never met a sane person who can visualize 4 dimensions, and you don't want to be one of the people who can. Now, the universe might also be light, and it turns out space naturally bends away from itself. You learn in mathematics about hyperbole. This is a universe in which lines travel on hyperbolas. So it's what we call hyperbolic geometry, or the shape of a saddle. And finally, there's the just right universe, the universe which is precariously balanced between the finite and the infinite. A universe where triangles add up to 180 degrees. This universe, less than 180 degrees. This universe, more than 180 degrees. What does a triangle add up to on Earth? Wrong! Everyone said 180 degrees. Huh? More than 180. Go use a globe and put 3 pieces of string on it and measure the angles. If you want to do it in your head, put one down on the equator, one down on the equator, and go up to the North Pole or the South Pole, depending on how you're inclined, and you can open that angle. You can't make it less than 180 degrees, but you can always make it more than 180 degrees. Geometry matters. All right, so I came to Australia at the end of 1994, and I was very disappointed. I said, God, I've just spent 3 years, 11 months, and 4 days measuring the biggest question in the universe. How old is the universe? Seemingly even maybe got the right answer. And then I realized that that wasn't the biggest question, because I didn't actually know how old the universe is. And if I figured out how old the universe is, I could also figure out its shape, its weight, and its future. Now that's a question worth asking. And that is the question I came to Australia to answer. And the reason I came here is because Australia was a great place for me to do my research. Mount Stromlo is one of the world's great observatories, and it was a place where I could go and work with a group of international people on this problem. And the idea was the following. Imagine I could do what I did for my PhD thesis and measure how fast the universe is expanding, and then compare my answer to very distant objects whose light took billions upon billions of years to reach us. Then I could look at how this number changed back in time. If the universe was empty, that is, that's the straight line where it just keeps expanding at the same rate forever, well, then the universe would be expanding in the past at the same rate that's expanding now. On the other hand, there is a dividing line, a critical value of the trajectory, of which on one side, gravity wins, and the universe is finite, both in time and space. The other side of that line, gravity loses, and the universe goes on forever. How are we going to go and do this? Well, I need big telescopes, but I need really bright light bulbs. And the brightest light bulbs we have are exploding stars. Not just an ordinary star, a star that explodes. And those stars we call type 1a supernovae. To understand what one of these objects are, let's look at the life of the sun for just a second. Our sun was formed 4.6 billion years ago, and in about 5 billion years or so, the sun is going to puff up and the Earth is going to be destroyed. The sun is going to collapse down to a tiny little star called a white dwarf star, about the size of the Earth. Now, if our sun was instead born as a binary star, that same process happens for the bigger of the two stars first. But stars are a lot bigger than the Earth, so they survive. And that means the second star will do that same process a little later, and that allows material to accumulate on the star, making it heavier and heavier, till it reaches 1.38 times the mass of the sun, at which point it becomes unstable to gravity. This is something Chandrasekhar calculated and won a Nobel Prize for. And it explodes with the force of 5 billion suns. These objects make the iron of the universe, 2/3 of it. So all the iron you see, 2/3 of them are created in these explosions. They take 20 days to rise and fall, and we can use them as these amazingly bright light bulbs. The first person to really do this was a man by the name of Fritz Zwicky, a very well-known astronomer. And he had a telescope brought over from Germany known as a Schmidt telescope. Not named after me or my family, but rather a one-armed optician named Bernard Schmidt, who was known to drink a lot and play with dynamite when he was a child. That's why he had one arm. But he was a very good optician, and he allowed Zwicky to take pictures not of just a tiny little piece of the sky, but pieces of the sky many, many times larger than the full moon. And when Zwicky did that, occasionally in galaxies, he saw these new stars appear, which he called supernovae. Novae are new stars. Supernovae are really bright new stars. And so in 1968, after 30 years worth of work with this tiny little telescope, at Caltech, went through and plotted the same thing Hubble did, bright versus faint, so near, far, low redshift, higher redshift, and they saw the expansion of the universe, no big deal. But the difference is this was a tiny little telescope, 18 inches across, and this diagram went out 1,000 times further than Hubble could go. So tiny telescope, much, much further, because these things are all really, really bright, 5 billion times brighter than a star. So that was the beginning. But a group in Chile went through, are the ones who made the main work, did the main work that allowed these things to be used in earnest. And what they did is they used the same technique that Zwicky used. They used the Schmidt telescope. They took photographic plates. This is in 1990. And I actually met these guys during my PhD thesis when they were doing it. They would take one plate, put it here, another plate here. There was a little lever, went back and forth. Click, 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 click. You put your eyes here and your brain sees one, the other, one, the other. We had very slow computers back then. The brain's a pretty fast computer. And this allowed your brain to pick out the things that had changed. So they searched the skies this way, and they discovered a whole bunch of exploding stars, but they had a new thing up their sleeve, digital detectors. Photographic plates are great for taking pictures, but you don't know how bright things are because they're not very accurate. Digital detectors are very accurate. You count photons, 1, 2, 3. Photographic plates go, bunch of photons, suddenly, okay, crystal changes form. So it's a very nonlinear process. Useful, but digital is better. So they went, and one of the team came up and visited me at Harvard. Actually, I came down and visited them first, and they were very depressed. And the reason they were depressed is that this is one of their first light curves, of how bright the supernovae is over time. And it turned out this object was a lot different than the other objects they had studied at the same distance. It was fainter, so it was clearly saying these exploding stars, which had always thought to have been almost identical, were not identical. So they were sort of at the point of despair and saying, what are we going to learn from this? And then Mario Hamwi from this team came and visited us at Harvard and showed us their new result. And their new result showed that there was a trend that objects that rose and fell quickly were fainter than the ones that rose and fell slowly. Turns out these form more iron, these form smaller irons. These are bigger atomic bombs, these are smaller ones. And so when he came and showed me his Hubble diagram, I had just finished mine. This is about 9 months after I finished mine. And I looked at his and I said, wow, all his points lie on the line, unlike mine, which are a little messier. And I said, wow, you guys really know what you're doing, because this meant that they have been able to calibrate how many watts these things were to amazing accuracy, to better than 10%. And my wattage was calibrated to about 35%, and I thought I was doing pretty well. So I dropped what I did and started working with this team, as I'll show you in just a second, to go through and extend these really bright objects further and further into the past. This team eventually found 29 such objects, and they provide the basis for the experiments I'll tell you about. Now, it turns out 1994 was significant not just because of the work in using and calibrating how many watts these objects were, but also because another team based in Berkeley had started using the new technology, big telescopes and digital detectors, to look for these exploding stars in the distant past. Now, we didn't think they knew how to use them, but they knew how to find them. And so once they started finding them, we knew all parts of the discovery process were in place. And so I was down in Chile just before I moved to Australia, and here we are discussing the experiment that would become what we call the High Redshift Supernova Search, the program that we use to march back and measure what the universe was doing in the past. Proposal went in, and I moved to Australia. So one of the great things were the digital detectors, but the other thing were the new telescopes. In 1994, the Keck telescopes, the new 10-meter telescopes, still the largest working telescopes on planet Earth, were able to get their first light, and they enabled us to take spectra, something we needed to do, of these distant exploding stars. Because remember, we need to know how much the universe has expanded, we need to know the distance. And so these telescopes were the first that really allowed us to measure how much the universe had expanded between us and these exploding stars, because these objects are very faint because they're so far away. And the digital detectors, well, here's what our detectors looked like back then. These are CCDs, analogous to the things that are in your smartphones. It turns out use a slightly different technology now. These are still used in video cameras sometimes. And we had our first 4 megapixel CCD cameras in 1994. Now, 4 megapixel now doesn't sound much, but it was 1994. Your iPhone is about 100 times faster than any machine I had access to in 1994. And yes, your digital detectors are 2 times bigger than we had access. So we took lots of data with these things, and they really transformed our ability to look at enough sky to find the very rare supernovae that we were after. So this led 2 teams, one led by Saul Perlmutter, the guys who were trying to find the distant objects, and one led by myself, the ones trying to make sure we understood how to measure distances actually, to compete with each other. We did try to work together. Turns out you don't always find common ground. This is a particle physics community. We were astronomers. We had different ways of doing things. But the competition was good because it made sure we worked faster and we were more careful, and it meant we always knew that if we made a mistake, someone was going to be there to tell the world exactly how stupid we were. So the challenge of finding these objects was really hard. Here is 1/8 of one image we would take, and we would take 1,000 images like this a night. And the key is to find the needle in the haystack, the exploding star. So look there and say, can you find it? Well, I'll show you where it is. It's right there. It's this little guy. And how do we know that? Because we take not one image, we take 2 images. We take a before and after. So here you can see in a period of 3 weeks, nothing became something. Now to do this, my job was to write the computer programs that would sift through all the data, line up the data and subtract it, and then look for the little blips which were left over. It's not so hard now, but it was quite a challenge back in 1994, I assure you. This object, just to give you a scale, was 5 billion light years in distance. That is, it exploded before the Earth was formed. That is the power of astronomy. We can't look forward, we can guess forward, but we really can look into the past. So to give you a sense, I take you to Chile, to the CTIO 4-meter, the sister telescope to the Anglo-Australian telescope near Coonabarabran. That is a person from the other team, silhouetted in black because he's the bad guy. We used to share the telescopes because we were all using the same facilities because they were the best ones in the world. Astronomers share their telescopes. So as the sky goes by, you would have seen Nick Sunsef, who co-founded the team with me. We're taking data, making sure everything is just so. We get 6 nights a year. You screw something up, that's the end of your career. So you really got to be careful. My software is processing the data, looking for things, but it finds a lot of stuff. It finds supernovae, but it finds all sorts of things like asteroids, flare stars, and glitches. So we have a sweatshop of people looking at each candidate, trying to say, did Brian's software get it right, or is this just a mess? So time is of the essence because 18 hours later, on the other side of the planet, we have the Keck telescopes teed up, ready to take data on these things. And so we had a huge amounts of data to go through, like 50 gigabytes a night. Again, doesn't sound bad now, but it was a lot back then. And there at the Keck telescope, as we take our data, who's there? Saul Perlmutter from the other team, because of course he's using that telescope too. So the competition was fierce, but we did often get to go out and have drinks with each other afterwards, although we did keep our finding charts of our discoveries to ourselves. So in the end of 1997, beginning of 1998, we were looking at our data, and this is what it looked like. Adam Rees, who was working at Berkeley at the time, sent me a plot that looked more like this. And what I show you here is a measure of the expansion rate of the universe from each supernova. These objects here are the nearby ones. They're the ones from the Chilean group. A little bit there from another group as well. And each one has an uncertainty, so 68% of the time, the correct answer of the expansion rate of the universe lies from here to here. And you can see if you take an average with your eye, you can't really see what's going on. They could be here, they could be here, you can't really tell. But the distant objects, well, that was interesting, because not a single one was consistent with a universe that's finite. Every single one was above that line. And then when you look on average, you realize that, well, some lie in the yellow part. On average, they lie above the line. In this part of the diagram, where the universe is not slowing down over time. Instead, it's speeding up. Now, to look at this data, you have to do a statistical analysis. And the statistical analysis we did said that 3 out of 10,000 times, this could be a statistical fluke. 3 out of 10,000. So we were 99.9% sure, but particle physicists like to be 99.999999. That's why they take $8 billion to make a discovery, and we tend to spend 8,000 to make our discoveries. It also means why they don't make as many mistakes as astronomers do. So it turns out we weren't the only ones who were getting this answer. But people often ask, when you saw this data for the first time, did you go, eureka? And the answer is no. Adam Rees, when he said it to me, I said, Adam, oh dear, what have we done wrong? We've clearly made a mistake. We need to check our work and go through every piece of it, piece by piece, and see what we get. We did that. The answer didn't change essentially at all. So imagine our surprise when we suddenly found out that the other team was getting the exact same crazy answer we were. Independently, we didn't know about each other. So in 1998, 2 papers were written. Here they are, and they show the members of the team. And here the team is together for the first and only time at the Nobel Prize ceremony in 2011. Now, I'm sad to say that you will note that it's a pretty blokey group up there. Astronomy has a long history of being very male-dominated. I am proud to say that is changed rapidly. Half of our graduate students at Mount Stromlo are female. Unfortunately, when I started in 1995, there was like 1 female graduate student. So it takes time for things to change, but things are changing for the better. And we weren't the only group there. The other team, fortunately, was a little less blokey than us. They were there at Stockholm as well, celebrating the idea of an accelerating universe. Now, I realize that one thing I would have appreciated before I won a Nobel Prize was a little idea of what it was going to be like. And so since I know you guys need to know this, I'm going to go through a little bit. So when you arrive in Stockholm, you don't get to go through customs. No, they're going to pull you to the front of the plane, and they're going to confront you with a driver. A BMW, interestingly enough, in Stockholm. I asked what happened to the Volvos, and they said, that company was bought by China, so we're buying European now. I said, okay. Anyway, my driver's name was Stig. For the Australians in the audience, you'll understand the irony of that. Stig, my driver, got us around the streets of Stockholm quickly. You get to meet the king. He presents you your award in front of live television. People in Sweden always wanted to know, what exactly does the king say to you? And he says to you, congratulations on behalf of the Royal Academy of Sweden. And in my case, because I have a vineyard and a winery and I make wine, and I'd given through the embassy him a bottle of wine, he said, thank you very much for the bottle of wine. It was very nice. So that was a nice little thing. And the other thing the Swedes do, at least in my case, is they give you a princess. So Crown Princess Victoria and I got to have dinner together. As I told my wife when I saw this picture in the newspaper the next day, I said, gosh, I look so glamorous with a princess on my arm. She wasn't very pleased with that remark. But anyway. So the interesting thing is, what is pushing on the universe? Well, our best idea comes from none other than Albert Einstein. That fudge factor, the cosmological constant, energy as a part of space, seems to explain exactly what we're seeing. The only problem is we need a lot of this stuff. Now, we don't know for sure that it's Einstein's cosmological constant, so we give it a euphemism, which we call dark energy. Dark in astronomy is a euphemism for we really don't understand. So we really don't understand energy. It seems to be what the stuff is. So the idea of dark energy is that if you go through and do a detailed analysis of our work, that you need the universe to be a mix of about 30% which pulls on the universe and 70% of this dark energy which pushes on the universe. Of course, that required people to believe that we were actually right. And the way astronomy or science works is when people get a crazy answer, everyone doesn't just celebrate and give you the Nobel Prize immediately. Rather, they want to test and see, did this person's work, does it stand up to scrutiny? And I have to admit, somewhat skeptical about this. I mean, I knew what my data said, but it seemed too crazy to be believed. And one of the first things was done here in Australia. It was a major analysis of the southern sky, where they went through and mapped out 221,000 galaxies from the Anglo-Australian telescope. And the map, you can see, looks like foam. And there are places we call voids where there are very few galaxies, and there are places where there are lots of galaxies. It turns out that this foam is created by gravity pulling on matter in the universe to form the galaxies. And we can use the theory of gravity to very accurately measure how much gravity there is in the universe. At least the gravity that makes things pull type. The stuff that makes stuff push, turns out, doesn't affect this at all. So this team in 2001 went through and weighed the universe very accurately. And what they found was that the amount of gravity pulling on galaxies is 27% of the stuff necessary to make the universe flat or just right. Remember, the shape of space depends on how much stuff there is in the universe? Well, that's how astronomers weigh the universe. They compare it to how much stuff it takes to bend space so that it's flat. Their measurement was the gravity in the universe got you 27% of the way to making the universe flat. But that was an interesting measurement because it confirmed what was an age-old problem. That was 5 times more gravity than we could account for in atoms. That is, for every atom's worth of gravity, there was 5 times more gravity. And that leads to our second euphemism, dark matter, or, we don't really understand it, matter. So what is dark matter? Well, dark matter could be some sort of undiscovered particle, like a neutrino that can travel right through the Earth. So right now in your body, neutrinos are passing right through you right now. These are what we call weakly interacting, and they are called that because they weakly interact. They tend to go right through, for example, a light year of lead. So we know those neutrinos work, but exist, but it could be that there is an undiscovered particle, which we haven't yet detected, which is zooming through our body right now. So it has gravity just like atoms, but it's essentially invisible, because the only way we know things are there is because they interact. The other experiment came from the cosmic microwave background, that afterglow of the Big Bang. Here is the map of the sky, and these are sound waves splashing around the universe. Think of it that the Big Bang is like taking the universe and throwing a bunch of gravel into it. And you get all these waves and puddles splashing around, and looking at how big those sound waves are tells you the speed of sound times the age of the universe. Now, the universe here is not that different from what the universe is here on Earth. We can create the conditions in this picture more or less in the lab. So we know what the speed of sound is extraordinarily accurately. We know the physical equations very accurately. So we can calculate how big those sound waves should be with amazing accuracy. And remember, the further away something is, the smaller it appears. Well, that's not exactly true in a curved universe that's expanding. But one of the big differences between a curved universe and a flat universe is how big things appear. And so, for example, this ruler appears the same size in the yellow and the red line. But in one case, you see a small ruler, the red one. In the yellow case, you see a large ruler. That's a little confusing. Think of it as looking into a rear view mirror, which is curved. It distorts what things look like. The universe is curved. It acts as a lens or a mirror, very analogously. So it turns out objects appear larger if space is curved onto itself. And so that means we can go and look at those bumps and wiggles. And if they're small, the universe has got hyperbolic geometry or is light. If they're big, the universe is finite and has lots of stuff in it. but it turns out it's just right, and it's just right to better than 1%. That means if you add up everything in the universe, there's enough stuff to get you all the way to making the universe flat. This experiment doesn't care about if the stuff makes gravity push or pull. It's sensitive to anything in the universe. So that allows us to do a little cosmic subtraction. Everything adds up to 100%. 27% of it is gravitationally attractive, leaving us with 73% mystery matter. Seemingly the same mystery matter that we see pushing the universe apart. So where does this leave us? Well, it leaves us with a mess. It leaves us with a universe of which 4% are the atoms we know and love and are made of, that we observe through the universe. Everything else, the other 96% of the universe, is stuff we do not understand very well. A large fraction of it is this stuff we call dark matter, but most of it is this stuff we call dark energy, the stuff pushing the universe apart. Now you might say, if you have to make up 96% of the universe, doesn't that just mean you don't understand what you're doing? And that would be a very reasonable point of view from your side. But the amazing thing about this model of the universe is it has been able to predict every single observation we have been able to make over the last 15 years. And reality is a little more complicated than we think of in our everyday lives. Reality is ideas that predict things. And as long as an idea always predicts things, and it's the simplest possible idea, that's what we think reality is. An example is gravity. Before Einstein, the reality was gravity is pulling things together. Einstein comes along, gravity is warping space. Now, you guys haven't been taught general relativity. Most of you, anyway. So, when you think of this as having gravity, do you think of it as space being warped around it? Or do you think of it as gravity pulling? You almost certainly think of it as gravity pulling, which is the same way I think of it, because it's simple and it works. But that isn't reality. Reality is something different. And we know Einstein's theory of general relativity doesn't completely work properly. So we're probably going to redefine reality in the future as well. So we have two things in the universe. We have dark matter. And dark matter has the interesting effect, that is, the more the universe expands, the lower the density of this stuff is. That is, if I have this stuff in a box, and the box gets bigger, the density in the box gets smaller. Dark energy, though, is funny. Dark energy seems to be part of space itself. So as the universe expands, dark energy gets created with the created space, so its density doesn't change over time. It means that over time it will become more and more important relative to the atoms or even dark matter that has gravity. To think of it this way, we can look back in time, and if you look back in time, you will have dark energy have smaller and smaller effect because its density stays the same, but the density of the atoms, the hydrogen atoms inside the box, raises back in time. So we really have a battle for domination of the universe. It's dark energy versus dark matter. And the future of the universe, well, the universe's battle has been won. The future of the universe is dark energy. It seems to have taken over the universe about 6 billion years ago. And the more it expands, the more it dominates. So, because the more space expands, the more dark energy is created, that creates even more space because it can push even harder, which allows there to be even more dark energy, which can push even harder. So you get a runaway process. It turns out eventually the expansion of space happens even more quickly than light can travel through space. So for example, a perfectly happy galaxy we can see now will have so much space created between us and that galaxy over time that the photon that it emits will travel through space and get stranded by the expansion of space. It will never be able to reach us. So things we see now will not be visible in the future. Now, one thing to think about is that we are not expanding right now. And the reason we're not expanding right now is because the battle for this part of the universe ended 13.6 billion years ago, because there was so much stuff in this part of the universe in the form of atoms that we were able to collapse down to form the Milky Way, to form the Earth. The amount of dark energy in this room is 30 orders of magnitude below the density of atoms. So the thing that atoms can do is they can conglomerate and form things. Dark energy can't do that. It's always stuck at the same level. So that is why we are not expanding. We are going to live in the future in what we call an island universe. Because attractive gravity has won the battle here, it hasn't won the battle beyond our galaxies. And so eventually everything but the galaxies that are gravitationally bound to us will be so far away we won't be able to see it. So, for example, in 3.5 billion years, the sky is going to light up as the Andromeda galaxy and our own galaxy merge. It's not a train wreck, because remember all that space between stars. Rather, it's like the merging of two swarms of bees. But in the end, we're going to live in a galaxy that has no gas. It's going to be kind of a boring galaxy. But beyond that, we will see nothing. We will look out onto a universe void of anything. No stars, no galaxies, nothing. Now the reality is, we don't really understand dark energy. And until we understand what's accelerating the cosmos, anything is possible. Dark energy might change in the future, speed up or slow down. It can do almost anything a theorist wants if you give them a pen and paper. Never give theorists pens and paper. One possibility, my favorite, is known as the Big Rip, or, if you prefer, the Big RIP, as in rest in peace. If, for some reason, a theorist, given a piece of paper, can dream up a form of dark energy which gets created a little faster than the universe expands, that is, if I double a piece of space, I get more than double the amount of dark energy, then the energy of the density of this dark energy increases over time. Eventually, it will be more dense than anything in the universe, allowing it to rip you apart at the subatomic level. It's quite a remarkable universe, because as you look onto it, you will suddenly see towards the end of the universe, stars start disappearing. Then one day, the sun disappears. And then the end is very near when that happens. The whole ending happens in a human lifetime. But you'll be glad to know not for another hundreds of billions of years, if it were ever to happen at all. This is a very speculative. You should not think that this is the way the universe is going to end. So that would certainly leave nothing, at least a good definition of it, where every subatomic particle is separated by an infinite distance from every other subatomic particle in the universe. It certainly would be a very boring subatomic particle universe. Anyway, whatever, unless dark matter or dark energy suddenly disappears, it does seem that the universe will continue at an ever-increasing rate to expand and fade away. Meaning people like myself, cosmologists, will be unemployed in the future because we'll have nothing left to look at. I'll stop there.